Hello, my name is Prachi Patel, and my video is on a phenomenon called piezoelectricity. So what is piezoelectricity? Piezoelectricity was first discovered by Marie and Pierre Curie in 1880, and it's a phenomenon where a mechanical force applied to certain materials can generate an electrical voltage that is directly proportional to the amount of mechanical stress applied. The opposite is also true. If you apply an electrical charge, the crystal will also distort physically. Piezoelectricity is seen in a variety of materials like crystals, ceramics, and organic molecules, and also more. Examples of crystals would be quartz, tourmaline, and Rochelle salt, which you can see on the right. And ceramics would include lead zirconate titanate, also known as PZT, or polyvinylidene fluoride. Examples of organic molecules would be Piezeo-1, which is a protein that can be found in your bladder, where, for example, pressure signals to the brain can let you know that you're peeing. So the way that piezoelectricity works is that you have a crystal lattice in which the unit cells remain neutral overall and in balance normally, but when a mechanical force is applied to the crystal, it makes the unit cell disfigure and temporarily polarize. And so that's what you can see with like a force has been applied and the crystal is disfiguring. And so the charge difference caused by the polarization then impacts the unit cell right next to it. And this creates like a charge moving through the crystal, which creates a temporary voltage. It's also important to note that if you strike the crystal, you will generate a temporary voltage that corresponds to the strike, but a constant pressure won't produce a constant current. Something you can see in the diagram here is that you need like something like the ion in the middle, which is like titanium or zirconium according to this diagram, which moves with like force applied. It doesn't necessarily have to be like titanium or zirconium, but you need some sort of, you need specific properties in the material structure in order for it to be a piezoelectric. And so one of my first thoughts when I was first reading about this was, does the crystal ever run out of electricity or like out of juice or something like that? And the answer is no, because it's kind of like how the photoelectric effect works, where the electrons are moved around, but they aren't being destroyed or anything crazy like that. And the movements of electrons themselves, like that is electricity. And so yeah, it's not gonna run out. So how can it be used? Today, it already has a lot of functional uses. An example would be piezo's in quartz watches. So if you've ever seen like quartz written in small letters on a watch face, it's probably a quartz watch. And they work where if you supply an electrical current to a piezeo in the watch, the piezeo will oscillate, and this vibration is then translated into the mechanical movements on the watch face. The relationship between vibrations and then therefore sounds and then with electricity in piezo's means that they're also used in microphones, radios, and also used to be used in earpieces. And then uses where energy can be generated for later consumption using piezo's, this is also called energy harvesting, include sidewalks with heavy traffic. So for example, they could be used in big cities. An example of this has been implemented in France. And then roads. The piezo's in roads could be really useful because you can remember that the amount of mechanical stress applied is directly proportional to the voltage produced, and automobiles are very heavy. A place where this has been implemented is in Israel. And then Japan went viral in 2008 for having a Christmas light display at train stations which generated light from piezoelectricity. And then as far as shoes are concerned, you can find an interesting array of science projects where people have tried to charge their phones using piezo's, where the piezo's like generate electricity because of like the pressure of footsteps. And I also found an interesting book discussing using energy from raindrops, which wouldn't necessarily generate a lot of electricity, but it is energy that otherwise, like the energy of the raindrops hitting the ground is energy that would not otherwise be used at all, maybe. Energy efficiency. So piezo's don't pop up super frequently as a major source of alternative energy, and it's for a good reason because it's really not effective enough to compete against the leading sources of energy, and it's especially not in the realm of fossil fuels. For example, a page at stanford.edu calculated that you would need to have like 20 people dancing to power a single standard 100-watt bulb, and so yeah, it's just not very efficient. Despite this, Piezoes can be used to harness the energy from things that we would otherwise not get energy from, things like people's footsteps to the weight of cars. Um, and even though it's like on a small scale, piezoes are inefficient. When they're implemented in places where large amounts of people naturally congregate and are moving around, you can at least reduce the amount of energy that would otherwise maybe come from a non-renewable source. Environmental impact. So while piezoes have their merits, the production of the materials themselves has the potential to be harmful. For example, one of the most popular materials, PZT, has lead in it. And there are movements for electronics to no longer have lead in them because they produce a large amount of heavy metal pollution, especially when electronics are dumped without regulation to less developed countries. The lead can then like leach out into the water supply and out of the dumps and poison wildlife and humans alike. And while usually the lead discussed in this type of in this topic is coming from the lead in soldering used on circuit boards, there is lead in PZT. And so there is motivation in the field to find good lead-free piezoelectric materials, which ideally are made using less energy than PZT. And then naturally occurring piezoelectric crystals can also be harmful to the environment because they're going to be mined. The mining for quartz in particular may be relatively less harmful compared to other rare materials, but mining in general is just bad for the environment. It disturbs nearby ecosystems, can cause water pollution, erosion, deforestation, and more. So in conclusion, piezoelectricity is an interesting phenomenon where mechanical stress can be used to harness energy and vice versa, but it is relatively energy inefficient. And while it's promising, it might be promising in the future with more development. The efficiency of a material should be compared against the harm of getting the materials in the first place. And at the same time, it's good to note that increased interest in these materials will lead to more research and development. And this could eventually lead to more efficient ways of harvesting energy using piezoelectricity. So here are my references, and my academic sources are in the discussion post with the link. Thank you for your time.